This is the original unstable glider. It is longitudinally statically unstable because the CG is located aft of the aerodynamic center, and there is no horizontal stabilizer. A properly designed and placed horizontal stabilizer aft of the CG counteracts the moment. This horizontal stabilizer design process will be highlighted in this presentation.
In order to make the glider longitudinally statically stable, we used an iterative design process. We began by creating an airfoil and a fuselage. Then, we determined the CG of the glider without the horizontal stabilizer by balancing the aircraft on a fulcrum. Assuming the mass of the stabilizer to be negligible to the overall CG, we proceeded to calculate the area of the tail required to counteract the moment due to lift of the wing. We assumed an aspect ratio for the horizontal stabilizer, then back calculated the span and chord. We then built and tested our design, learned from mistakes, and iterated to make corrections. The first step was to select and manufacture our airfoil. On the first design iteration of the glider, the initial wing was made from a thick airfoil and had an aspect ratio of 6. With this wing, we calculated the appropriately sized horizontal tail and found it required either an enormous volume fraction or lift curve slope in order to make the glider stable. We also made the mistake of assuming that thin airfoil theory was applicable to this 18% thick airfoil, which is not correct. These incorrectly estimated our aerodynamic center and lift curve slope. Therefore, we had to iterate our airfoil design to decrease the thickness. The next step in stabilizing the glider is to use the neutral point equation as derived in class to solve for the tail area. These equations will be discussed later. With a tail lever arm and aspect ratio selected in the range of recommendations provided by several sources, the dimensions of the horizontal stabilizer can be calculated. Here is the stabilizer design on our first try. We plotted the horizontal tail to scale on a computer and held the glider up to the computer for a practicality check and found that it looked silly. Anyways, we built it. And it didn't work because we had an error in our equation. These are the correct equations that we used to successfully stabilize our glider. After deciding that we desired a reasonable static margin of 15%, we used equation 1, the static margin equation derived in class, to determine the neutral point. We then used that neutral point value in equation 2, the neutral point equation. Then we calculated the tail area. We neglected downwash and assumed the dynamic pressure ratio, eta, to be 1. The lift curve slopes for the wing and tail were calculated and will be shown later. Finally, with the tail area and aspect ratio, we backed out the stabilizer dimensions as shown in the scale model in the gray box at the bottom of the screen. This is the horizontal tail that we built based off of our calculations. To ensure a lightweight structure, the base was made from coffee stirrers in the form of a truss system. Then, these coffee stirrers were laminated with packaging tape. Next, a drinking straw was used as a spar to help hold a consistent airfoil camber throughout, after we shaped a manila folder over the upper surface to form the upper surface of the airfoil. Because we found the thickness of this to be approximately 10.9%, we applied thin airfoil theory to assume a lift curve slope of 2 pi and an aerodynamic center located at the quarter chord of this thin airfoil. Here are the specifications for the new airfoil design. The original airfoil was compressed such that the thickness reduced from 18 to 10%. While this is approximately the NACA 2210 airfoil identified with airfoiltools.com, which has its own unique lift curve slope, we used the thin airfoil theory assumption to estimate the aerodynamic center and lift curve slope of this airfoil as the quarter chord and 2 pi respectively. We then used the same plan-form dimensions as the original unstable glider that you saw earlier, such that the aspect ratio was 6, the span was 23.5 inches, and the wing had a 3.875 inch chord.
Here we correct the airfoil lift curve slope for 3D effects. We assumed an Oswald's efficiency factor of 0.88 due to the primitive design of the wing and the low aspect ratio. The lift curve slope was reduced by 28% as a result of this.
Next, we corrected the horizontal tail's lift curve slope for 3D effects. We assumed an Oswald's efficiency factor of 0.85 due to the again primitive design of the surface and the very low aspect ratio of 3.8. The lift curve slope was reduced by 39% due to 3D effects, since the aspect ratio is just so low for the horizontal stabilizer. In the plot on the left, we illustrate the reduction in lift curve slope from the thin airfoil theory assumption of 2 pi shown in black. You can see how the horizontal tail's lift curve slope, shown in red, is in fact 15% lower than the wings, shown in blue. An estimated zero lift angle of attack of -3 degrees is shown solely for demonstration purposes of this plot.
Here is a dimensionalized photo of our final design. The center of gravity, aerodynamic center of the wing, and the neutral point have all been labeled. The center of gravity lies forward of the neutral point, ensuring stability.
We flew the glider at different CG locations. In this case, the CG is behind the aerodynamic center, and the glider has no horizontal stabilizer. After being launched at a small positive angle of attack, there was a disturbance which pitched the glider nose up, further increasing the angle of attack, since dCmD alpha is positive. This is because the glider is longitudinally statically unstable and will pitch up further until the glider stalls or flips over backwards, resulting in a crash. We attempted to get the glider as close to neutrally stable as possible. Because the CG is just slightly ahead of the neutral point, the glider is approximately neutrally stable. You can see how there's no real tendency of the glider to correct the pitch disturbance that is apparent near the end of the video. It is not sensitive to pitch disturbances. In order to move the CG forward, mass had to be added ahead of the current CG. To do this, we gathered some advanced materials we had on hand. We then attached this bundle of weights with a next-generation adhesive called packaging tape. With the CG now moved forward, we can demonstrate what happens when the CG is far ahead of the aerodynamic center and neutral point. The plane pitches down immediately and crashes. Our main takeaway from this project is that moving the CG forward is a really simple way to make the glider more stable. This can be seen by the static margin equation provided. As xCG becomes lower and lower, that static margin increases. And as long as the CG is aft of the aerodynamic center, it satisfied the requirements for this project. Additionally, we found that producing a horizontal tail with an especially small chord is difficult to shape without having a significant amount of structure for the stiffness required for the actual surface to maintain its shape in flight. Our first stabilizer attempt had a very small chord, about an inch. Therefore, getting any real airfoil shape with this little room is really difficult. So we iterated and used the truss structure as previously discussed to stiffen the new horizontal tail. We also picked a static margin such that the tail dimensions were practical to manufacture, paying close attention to the chord. And we finally ended up with a stabilizer of 9 by 2.375 inches for the chord.